I thought I will start out with making some really general remarks, which for the most part will reinforce what has already been discussed in the morning, and more particularly what my colleague Dave Yogi really said. So let's start out with, I just have a few slides since I've been given only 5 minutes. So, one of the issues, obviously one of the most important issues, especially from a hydrology viewpoint, is drought science. Now, there are 4 issues I thought are important to go back and revisit. The drought characterization. I think it was clearly articulated that this is one area where we still need to do a little bit of work. We still are not able to uniformly characterize droughts in space and time. And more importantly, and I think this came out a lot more clearly in the presentation that my colleague and friend, Professor Kabas, presented, the mechanisms. Much of the emphasis in drought over the years has been on data analysis and basically data crunching. But how drought essentially is triggered by combination of atmospheric mechanisms with the land surface processes in conjunction with anthropogenic changes, and how the entire science, the biology, the chemistry, the physics govern and are impacted by this phenomenon is something that we need to look at. And then of course the modeling part, incorporating in a comprehensive manner these mechanisms, and then of course the prediction, which is what we are doing, but the forecasting is altogether a different story. It is, even though we are doing forecasting, but this forecasting, especially far in advance, 5 years ahead of time, even 2 years, 3 years, 4 years ahead of time, is a long way to go. Now, I think in order to do the science, it's very important that we take a lot of measurements. And this is one area where we are severely deficient, particularly in the area of soil moisture, in the area of water quality, in the area of air quality, but even more importantly in the area of human health effects. There is hardly any data, even in economic terms, even though we frequently come up with losses, particularly economic losses or losses in the agricultural sector, but I'm not so sure about those numbers. Nobody tells me how reliable those numbers are and how exactly did they come up with those numbers. Now, but even if you start believing those numbers, and perhaps we tend to believe, but we are looking at a whole host of other costs associated with human health, associated with the loss of species, damage to the ecosystems, and the social issues, the loss to the social fabric of the society. This is something that I think we need to pay attention to. The other area, of course, this was discussed, data sharing and of course updating, so I will not go over. But coming back to this, now as I said, in terms of economic losses, we provide the numbers, but how exactly do we quantify the varied effects of drought episodes, not only in economic terms, but also more importantly in terms of ecosystems, in terms of health, social unrest, and also, political repercussions, because remember, politicians have a very narrow time span, narrow attention, which is directly tied with the election year cycle. And a lot of politics are impacted by the way the droughts are managed and the social impacts are managed. And I think we need to start collecting data, and we need to start coming up with by which we can quantify those impacts. Even more important is the communication. And of course, I was very, very pleased to learn about the way the communication mechanisms are being built into DRINET. But really, how do the effects get translated into common, easy to understand language, and certainly in terms of numerical values, because a person, a common man, a farmer, or even a common lay person does not quite understand the language of probability, the language of uncertainty, or the language based on SPI or PDSI. They are not interested in all this. They should be actually given in simple, easy to understand language some numerical values. And obviously, in order to do that, this uncertainty quantification has to be communicated. But again, it has to be translated into a very simple language. A farmer needs to know what exactly he will be up against in case of an eventual drought next year, 6 months from now, or whatever. He's not interested in an overall state averaging or regional averaging. That's not really his interest. His interest is what exactly is going to happen to his farm and how much loss can he expect with certain amount of uncertainty and so on. And the same thing applies to policy and decision making. The politicians do not quite understand, and of course we as scientists and engineers are not really good at communicating what we do. We do an excellent job if you draw a pie down up to about 95%. But in this 5% arena, we seem to be so deficient that we leave it over there, we write the articles, publish them, but we don't really take the next step to translate what we do in simple language so that it can be integrated into policy and decision making. The other thing which I will say is that if we want to really make a headway, it's very important that all stakeholders are brought aboard. And I think this point was emphasized, so I was very pleased to see that. I think these are some of the things I would say. And of course, again, besides doing the modeling, forecasting, communicate and so on, we also have to come up with strategies for reducing the impacts of drought. And coming from the water background, for example, we have to come up with easy to implement strategies. One way is doing things in an integrated water resources management manner, which really entails not only conservation, but also efficient use, treatment, recycling, reuse, development of additional resources. In other words, the point really of this slide is that there is no solution that we can prescribe which will fit all. We have to come up with local solutions where some solutions will be a lot better for one community or one locality or one region, and others for others another strategy might be more appropriate. So I think it is important that we take an integrated, comprehensive view. In other words, the problem is global, but the solutions and strategies must be local if we want to make a headway and have an impact of what we do on the well-being of the society.
All right, thank you. And thanks to the organizers for the invitation to come in and participate with you all this week. My name is Marc Savard. I'm a climatologist, and I oversee our monitoring program at the National Drought Mitigation Center. So essentially, a lot of our operational tools and development, including being one of the co-founders of the U.S. Drought Monitor back in the late 90s with Doug LeCompte. So with that, that's a hard act to follow there. He said about everything I was going to say. I think you'll see I have a lot of common themes in the 3 slides I have here. Having worked on this issue since the center formed in '95 with Don Wilhite there, these are the 5 big major challenges I've seen that I at least want to relay to you folks here today. One, we've heard a lot about it already, is the impact issue, both in collection of that information and in quantification. As Vijay said, even how states do it. There's no systematic methodology. You know, there's different multiplication factors that different economists are going to use to do this impact collection and quantification. So one state might call agricultural drought both crops and livestock. The next state might have an impact of an agriculture nature that does not include livestock. So you're never comparing apples and apples when you do that, and the methods are always different. Soil moisture, obviously in situ soil moisture is huge. The network has expanded somewhat, but it's still pretty woeful. I think you'll see as many, if not more, in the non-federal networks now as we have in our national network. The SCAN network for USDA NRCS is roughly 135 or 40 stations. NIDIS has funded around 100 additional stations through CRN through NOAA, so that puts us up to about 250 at 5 depths with redundancy at each depth down to around 100 centimeters typically is the standard. They're following what NRCS has recommended for the snowtail sites. And some of the snowtail sites up in the upper elevation are doing this as well, because we saw a situation back during the drought of 2002 in the West where the models were showing runoff values that were 30% more than actually happened, and they were going, where did that water go? Was it ablation? Was it lost to the soil soaking it up first because of inadequate, you know, and it's probably a combination of those things, but anyway, you know, the models were way off, and that just goes to show you we need some more in situ data, I think, to ground truth models and remote sensing data. Hydrology, both surface and groundwater. I think groundwater is becoming very critical to do a better job monitoring, not just quality, but also the, well, not just quantity, I mean, but also the quality. We've heard a little bit about that already. And then this whole application issue of remotely sense modeled and forecast issue data. This is something with being on the drought monitor team that it takes a while to sort of build up that community and that trust that a product works. You know, when I come into these type of meetings and I see some of the great potential products that DryNet's working on, we have to work with that to sort of transition it from research to operational. We have to build trust with who did it, how they did it, and how it works, you know, out in the real world. And then we have to deal with uncertainty, which is just the status quo. I mean, this whole stationarity issue that you've probably read about over the last few years with climate change is certainly something to consider moving forward. And then the one that always tends to get left out is what's the value of other systems, not just what we put economic value on, but what about the natural environment, the ecological system, and what value does that have, and what role does that play in the holistic circle and our interaction with it? One of my sayings is the last one there, if you've heard about the tree falling in the forest, mine is if a drought occurs in the desert, does anyone see it? So if you think about that a little bit, people think you can't have droughts in deserts. You can't have droughts in rainforests. But the truth is you can have drought anywhere, anytime, in any part of the world, because if you're not getting what you're normally supposed to get or used to, there can be impacts to the natural environment. And over the longer term shifts, then yeah, then maybe that's a climate change issue. But anyway, we need to be prepared for drought no matter what. So as far as the urban issue, we heard a little bit about that this morning too, or today. As of the last, not the most recent census, I'd like to see an updated map. I've seen some of the numbers and they come in quite a bit less than this, but in general they're still growing pretty rapidly. But you'll notice a lot of the dark greens aren't just in the West. We've got this issue in the southeast part of the United States, the big drought with Atlanta, the cartoon that had the state climatologist there, David Stooksbury, said, I think we have 54 flushes left or something like that. Georgia, Atlanta, one of the largest metro areas, very small catchment. All water flows out of Georgia, not into Georgia. It's a very small catchment system, so they're pretty vulnerable. And then in the West, when you see totals like 66% in Nevada and 40% in Arizona. Now again, those came down to like in the 30 to 35%, I believe, between 2000 and 2010, but it's still pretty unsustainable growth. It's not what I would call smart growth. But anyway, when you put all that together, it's definitely putting a squeeze on our water there. All right, so what do we do about it? You know, moving towards a resilient approach is a shift from crisis to risk management. That's what our center's about. So I'm gonna, by talking about this a little bit today, I'll be able to shorten my talk tomorrow, but steal some of my own thunder, if you will. We're about the proactive planning mitigation. So mitigation for us isn't the climate change terminology of mitigation, where you might be talking about GHG, emission reduction. For us, mitigation is anything you're doing in advance of drought to reduce your vulnerability or risk to drought. You can't stop drought from occurring. And a lot of that is providing information, education, translation of the science to the people, as Vijay talked about, supporting sustainable type of activities, and increasing self-reliance. I think we're very dependent on what can the government do for us, and a lot of times that's put us in sort of a vicious cycle that is a very hard paradigm to break out of, and we're seeing that yet today. Now, it will be interesting to see how the next farm bill evolves, but the talks of subsidies and such, that's usually a taboo subject. But something's broke. Our system's broke, and some things are going to have to change, I think. Some final take-home messages for me then. Again, that semantic thing, just talking between different groups, what do we mean by mitigation and adaptation and resiliency, and what do you mean by that? I think we have to be very careful with that. We have to do a good job of explaining ourselves when it comes to dealing with multi-hazards, not just drought, any hazard. How do we integrate various planning and modeling efforts for sort of a coherent long-term planning process? And again, that managing or planning under uncertainty, given non-stationarity. And my last slide is, I'm sure a lot of you have seen this slide, but really it's why are we here this week to talk about these things. There's a purpose and a reason that we're doing this, even if there's still skeptics among us. I think there's another one that they use with the dinosaurs that do a pretty good job, but I like using this slide because I think it really hits home, and I think that's what we're trying to find, our solutions. And it's just good to be here and listen to what y'all have to say. And with that, I'll turn it over to Chris.
I didn't do a PowerPoint, so we should leave up the comic, I think. And I just went through the list of questions and put down some thoughts quickly about each one, so I'll just share those with you. And so, the first question is, are we missing any data sources that can be added to drought monitoring that we are currently either not collecting or unable to incorporate? And I think we've had a good talk today on the SPI for Texas. That's a good example of this. I think one of the biggest issue is really not so much missing data in general as data integration. And we have a great host of satellite observations that we're really just struggling to learn how to use effectively. And usually those have a short period of record. So they have great, they're really exciting, people like them, they look like what they see on the Weather Channel, but they only have 4 or 5 or 10, 11 years of data. And at the same time, we'd like to specify drought in a nice quantitative way in terms of historical percentiles that go back 50 or 60 years and talk about a 1 in 30-year drought. And that can be tricky with a data set that's only 10 years old. And so I think developing techniques that allow us to bridge that gap are going to be really, really important. And one of the things that'll give us is the ability to look at droughts in places that we really haven't looked for them before. For example, in the Four Corners region, where dryness and land use changes might have produced drought and dust that can go to the snowpack in the Rockies and affect snowmelt. And without satellites, we've really never been able to track that kind of thing before. So I'm sort of a satellite plug, obviously, but I think learning how to use those techniques effectively will really help us into the future. And then again, of course, on data sources, I wrote down soil moisture, and I think everybody agrees that in situ measurements of soil moisture are really a critical goal for the future. And then a third item that I would add that I really don't think is very well appreciated by the drought community or the land data assimilation community is that the level of assimilation of different data sources, in my humble estimation, in land surface hydrology or drought assimilation is really quite far behind what it would be in, say, the meteorological sciences. So they're not always perfect, but if you look to meteorology as a example, there's very sophisticated approaches to taking multiple sources of information from in situ observations, from radiosondes, from satellites, and then using the physics of the atmosphere to try to come up with the best guess of what we're looking at. And we really don't have tools like that, at least certainly off the shelf, for looking at land surface hydrology. So I think that'll be another real challenge for the next 20 or 30 years. Moving on to the next set of questions. Can drought assessments handle uncertainty? For example, those as indicated in DryNet. And I had a few points about this that I think are important to consider. The first one is one of those happy thoughts, which is that, in general, in estimating rainfall, rainfall is heteroscedastic. The more you get of it, the more variable it is. Generally, the larger the error and your estimations of it are. And that actually, conversely, works to our favor when we're trying to monitor drought. When you didn't get any rainfall someplace, that's usually pretty easy to know. And so that's important. And I'm not sure that we do a good enough job of building upon that to communicate to our stakeholders, no, we're really sure that it just didn't rain here. And so I think that's moving forward, something that we can try to communicate more effectively. Another thing I think that probably many of you are aware of is that our knowledge about a drought shifts dramatically throughout the season. So as you're coming into the growing season in Indiana, by the time you get to June, you may have a deficit of rainfall. As you get to July, well, it's getting worse. And at some point, there's a real trigger where you're going to have a strong impact. And I think a lot of the experts know where those trigger points are. But I spend a lot of my professional career basically like on the phone or emailing, telling people, we reached the trigger point, we need to do something. And that's probably not a very effective way to communicate it. We need to kind of come up with methods that identify those moments and communicate them effectively. Something with InfuseNet that we're sort of limping towards that I think will really make some big advances this year are essentially presenting seasonal information as time series with sort of cones of uncertainty surrounding it, so that if you think about the performance of a crop, say, you start out the season with a big cone of uncertainty that's basically prescribed by climatology. And then as you get more and more observations, that narrows through time until you know exactly more or less what you're looking at. But we're just in the process of trying to develop those sorts of tools. And a fourth other component of a way to communicate uncertainty is in my work with rainfall accuracy and drought estimation accuracy. I'm really moving towards sort of binary kind of hit rates. So you define thresholds, and you look at how often you were right and how often you were wrong. And then there's a real literature about how you can assess accuracy. And I think that this can lead us to a good way to communicate it to end users as well. So for example, you can say, this is the worst drought in the last 30 years, take or minus a worst drought. This is one of the last, the 3 worst droughts in the last 30 years. And I think that kind of analog representation really helps people bracket the situation. Thinking about how uncertainty can be accepted in drought classification, what is the best mechanism for engaging the information into impact assessments and vulnerability calculations. I have to say that I am really, in my work, have a really tremendous respect for collaboration. And I think that it's really important to work with sectoral experts who are going to probably be better about taking the uncertainty in my information and incorporating it into the information in their product. And part of that because, we all think very complex thoughts, and when we're dealing with problems, we're really good actually at fusing many sources of information. And so, if I give off my meteorological data to somebody who's trying to estimate food insecurity in Kenya, and they're factoring in prices and the fact that the coffee market has gone up this year and the fact that, there's a societal conflict in this region, they have a really complicated thing if they're going to do an assessment. And so I think while we can speak quantitatively about how severe a drought is, meteorologically or hydrologically, at some point, doing it automatically is not probably very possible. At the same time, I think that one of the things that we can successfully convey is this idea of drought as a state of mind. That as we're looking out at the world and we're assessing the information, we begin with thinking, well, it's a El Nino, there might be a drought this year. Or, it looks like in Georgia, the last 10 years have been really dry, it might be dry this year. Sort of preconditioning conditions, and then we begin to monitor, and then our, certainty about whether there's an evolution of a drought increases. And so it's really a gamut, and there's not a simple declaration of a drought, but a whole series of steps of certainty. And I think it's important that we communicate effectively with our stakeholders at each of those steps. So then on to the fourth question, urban areas, which I don't know very much about, frankly. But I think one of the things that is often forgotten is that, at least in the developing world, is that these kinds of droughts can really directly put people at risk. So in 2009, people in Nairobi were digging wells in the streets. And a complicating factor that's probably even more dangerous are the related health risks. So if there's a drought in a lot of places in the developing world, and there's a reduction in water supply for the billions of people living in cities, that creates an increased health risk as well. And again, something that I mentioned and other people have mentioned as well is this idea of commodity prices translating risks across the world to people that are millions of miles away, thousands of miles away. And then coming to this last question, or fifth question, what longer-term resilience options are there for drought? I think clearly one that it's really simple, that was mentioned before, but that we should keep mentioning again, is to simply increase our efficiency to reduce demand. I mean, that's one of the simplest ways that we can increase our resilience. And so we should invest in ways to use water more efficiently. From a crop perspective, it takes basically as much water to produce a really low-yielding amount of maize or corn versus a high-yielding one. So there's lots of things that we can do to use the water that we are using better. Another component is we should think about how we develop and grow, right, whether it's population growth in Nevada or people in the Somali region of Ethiopia farming. We need to really try to reduce growth into areas that we know are going to be water insecure. And so just coming to the last point, where's drought in education? I would suggest that there's a bigger issue, which is where is climate or meteorology in education? I think that one of the reasons that we as a society are so poorly ready to cope with things like climate change is it's not taught. The response of the atmosphere to greenhouse gas emissions is not, kind of rocket science. It's a pretty straightforward response. But nobody is taught this, even in college. Whereas your average, high school student will have a year of biology and a year of physics, maybe a year of chemistry. So I think, in general, we should try to promote more climate and meteorology education in our schools. Thanks.
Chris, I don't have any PowerPoint slides, and I hope the ceiling holds out at least for another hour or so here. I don't know what they're doing up there, Dev, but it's...
Sending in some data.
Yeah. Well, I'm Jim Angel, the Illinois State Climatologist. I'm at the Illinois State Water Survey, so just right down the road, almost neighbors to Indiana here. And I just had a couple of comments in general, just kind of kick things off. First of all, I agree with everything that these guys have said, and that's maybe the disadvantage of being the last is everybody else has already said it. I'll just say soil moisture, yeah, that's one that we definitely need measurements on, and not only what's happening right now, but also having a historical context to put it in. What we've done in Illinois, we've got about 20 or so years of data, and if you kind of cast it as an anomaly, then you got to kind of get away from the fact that you got dry or sandy soils and not so sandy soils, and you kind of normalize across the region. So that's one way to get around that, but you do need at least some kind of a history to make that happen. So it's not just the real-time stuff, but actually having the historical record is valuable as well. Probably another one that we struggle with in the Midwest a lot is the impact on drought, short-term drought, especially on agriculture, and kind of like what Chris was hitting at there, that you get a situation where it's dry, turns dry in July and August, and it starts to get hot out. and you're trying to estimate what the impacts are on the crops, and you might use past experience as one rule of thumb, and sometimes that can fail spectacularly because the genetics have changed, the cultivation practices have changed, and even the situation from one year to the next can change enough that just because you know what happened in the drought of 1988 or the 2005 drought, that may not translate into what's going to be the impacts for the drought of 2011. So that's a real challenge, is trying to estimate the impacts on crops, and sometimes you don't learn about it until long after the fact. So you may look at the 2010 conditions, where you may not know the yields until maybe the next winter. So having like a crop models or better crop models would certainly be a big help in that regard. So I think that's another area we can work on. So there's various techniques on how to fill in some of the gaps there in that regard. Another thing I was going to talk about just briefly was, and Doug kind of hinted at this before, several of us worked on this project called Drought Ready Communities, and how many have heard of Storm Ready Communities with the National Weather Service? So the idea is storm ready, you make communities kind of, they're not storm proof, but it makes them prepared for severe weather in the Midwest. And I don't know if this is a Midwestern thing or across the whole U.S., but the idea is that it involves engaging the public and developing communication procedures, and then, once a warning takes place, who blows the siren and who identifies the shelters and all that good stuff. Well, it's the same kind of application towards drought. And so the idea is that you help communities rather than states or the nation. You actually go to the community level and focus on identifying who the stakeholders are and who the public is, and go through this exercise of talking about droughts in the past and what the impacts have been, where the vulnerabilities are, and then also roll into that, what's the role of communication, who's going to watch for the drought, who's going to watch the drought monitor, and who's going to watch the lake levels, and when it drops below a certain level, that's when we start a plan to reduce our consumption and things like that. So it was really kind of an eye-opening exercise for me, because a lot of times we kind of fall into this, what we call the expert level or top-down approach, where you get a bunch of PhDs in a room and they write a report by PhDs for PhDs. And so they a lot of times kind of collect dust on the shelf. So this case, we actually were in the field engaging the community from the get-go, and engaging the public. And I think that's a much more effective approach in at least in drought preparedness and planning, is to engage them from the very start. So with that, I'll stop, and we'll open it up to the panel discussion.
Thank you. All right, it's now time for the famous audience participation. Any questions from the audience? Yes,
We talked about the issue of data collection. After a drought has occurred, and then they say Texas lost $1.2 billion, California lost $3 billion. But, do we have, but the breakdown of it, it's like somebody telling me that the average rainfall in Ohio is 39 inches per year. No, that doesn't help. Don't we need to have some kind of breakdown? Can that be included, the impacts data? Can they also be collected and included in all the statistical and probabilistic analysis?
is this question directed towards anybody in particular, or?
No, the panel.
Yeah, we both can speak to that. Is it loud enough in the back? You can hear me? As I mentioned in my little intro there, there is no systematic methodology that the states follow, which causes lots of issues. And as Vijay mentioned, the methods of the multiplication factors, the economic side of it, because we actually have we have an economist on our staff, And it's like a whole nother world, man, trying to understand that and translate it, and how did you do this, and so there's a whole issue of sort of that cross-pollination of the economist and the physical scientist, and how they're doing this and taking this and using that. But to my knowledge, there's absolutely no systematic for drought anyway, I can say pretty certainly. It's funny how after a hurricane they can get in a helicopter and they look at structural damage, right? They have insurance, right? A lot of the land, there isn't that on a lot of acres, millions of acres. And drought has such a large footprint and it impacts so many more people. There's just not a good method out there. It's kind of the holy grail. If we can find a way to do that, we're very much trying to get states and work with NIDIS to kind of have sort of a basic systematic way that would at least be comparable between states. But I don't know if that will go very far. We've done it with about 15 states so far, and we'll keep trying. So I don't know, Vijay, if you want to add to that or not.
I think you said it right. I just, first, we really do not have enough data to start with. And whatever little we have, we are not even sure how exactly it is collected and how best it is analyzed. We just don't have. And that is one of the things that we as a community need to emphasize. I think, for some regions, maybe this has been one of the drawbacks of the so-called IT revolution, that we have moved away from making our hands dirty, going out there in the field and collecting the data that we really need to collect. This is true certainly in the water area, but this is equally true in other areas. For example, in health sciences also, it's very difficult to get a handle on the data which directly pertains to human health impacts. We just don't have the data. And if at all it exists, it's very difficult to have an access to it. And so, this is one of the problems that we have. And this is something that we need to emphasize. And even in the hydrology area, even, for example, even in the case of rainfall and stream flow, something that perhaps we have the best coverage of, even there, if we look at the historical trends, there has been a decided emphasis on reducing the number of steam gauging stations across the U.S. Likewise, we don't have enough of spatial coverage. So even though we do all kinds of modeling, but the fact remains that our modeling also has a great deal to be desired, primarily because of lack of spatial coverage with regard to data on various hydrologic processes. We just don't have. And so we are making all kinds of assumptions with regard to interpolation of the data. When we are constructing a map, sometimes, just like when a layman gets an output from computer, he or she starts thinking that is the truth. But the fact of the matter is that computer output is far from being true. The same thing applies to these very nice maps. And we tend to start believing without really going as to what has undergone in preparing the maps, as if these maps represent what the true picture is, which is really far from true. So, this is one of the problems that we have. Question?
Yeah, I have a comment for, the third speaker. And in general, the issue of soil moisture, a very critical component of the whole problem. And, there's already mention about remote sensing, of soil moisture, which basically would provide, some aerial, average estimates, if you like. And then, there would be in situ measurements. So the question would be, how to, in a way, marry those, reconcile, those measurements. And that's really a key question. And in fact, one complication with that is that the remote sensing would be only observing, the moisture, at a few centimeters, of the soil. Whereas, in hydrologic processes, we are really dealing, with soil moisture that would be effective, in runoff, even, to on the order of meters. Which brings me, to the comment that you made about hydrologic science. Now, in the grid scales, that one is looking at this problem, even if you go down, to say 1 kilometer, grid resolution, you have tremendous variability, in the soil characteristics. If you, even, within a 1 square kilometer, grid, you are going to see tens of soil surveys, if you like. Each of them, having different soil layers, with different, types, soil types. So the fundamental question that really needs to be addressed, in fact, from a very practical perspective, is, how to basically model and average out, the soil moisture dynamics. The interesting and very sad, fact is that in hydrology, in fact, there are such models, as it turns out. There are models, that do, average out the soil, moisture dynamics, both, in the vertical direction and in the horizontal scales, yet they are really not recognized by the governing, scientific community, if you like, of hydrology. Whereas, in atmospheric science, the advances in atmospheric science were actually recognized and adopted by the atmospheric science community. The sad fragmentation of the hydrologic community, I'm not going to go into the details, basically resulted in basically, ending up with the models that were actually created 40 years ago. The models, that were created, which were called like Stanford watershed model. Today, we are actually seeing the same model, being used, in different clothes, if you like, okay? It's the same thing, but in different clothes. What are called as like variable infiltration capacity model, VIC model, is nothing else but a cosmetized, Stanford watershed model. Yet, it's the hydrologic politics that is really in question. It's not the hydrologic science in question. There are actually models out there. In fact, I would refer you to some of the papers that are out there already. One of them is, in fact, by my colleague here, Professor Singh. There's a paper by him on mathematical models in Journal of Hydrologic Engineering, together with David Woolheiser. Another paper, that's really recent is by Steve Burgess and Camp and Steve Burgess on watershed models. The point is that the science concerning, the synthesizing, the remote sensing with the in situ measurements actually is already there. It's a matter of recognizing it, and it's a matter of using it.
I think I'm not sure this is a question for me, but I entirely concur with you, Levin. I think soil moisture, as I frequently call it, is really the gatekeeper, because this is the interface between land surface processes, which in turn interface with atmospheric processes, and the saturated subsurface environment, which is essentially lithological environment of groundwater. So this sits at the critical juncture in the hydrologic cycle. But this is absolutely true that we just do not have enough of soil moisture measurements in space and time. Now, even in the United States, this is true, let alone the developing countries. At least here you can get some soil moisture measurement. Now, of course, there is a website which has soil moisture measurements from all around the globe. But if you click the website, there is really not enough coverage. And also relating the in situ soil measurements, soil moisture measurements, to remote sensing, which, as Professor Khawas rightly pointed out, measures the soil moisture in the upper horizons, only up to a few centimeters. This correlation and doing the regression, there are all kinds of techniques which people have used. It's sometimes it works and sometimes it really does not work. But the fact remains that we have not invested as much in hydrologic measurements. It's as simple as that. And so
one of my colleagues in the panel indicated, Chris, with regard to the atmospheric science and the atmospheric science community in hydrology, in the water science in general. First of all, the water science in terms of research is of relatively recent origin. If you look at the history of science, atmospheric science is much older. The science of meteorology, people have been doing research for a far longer time than we started doing in the water science area. Second, that's a much more homogeneous community. Third, the amount of research, even at the federal level, that goes into atmospheric science is several-fold larger. In fact, it is more than 10-fold larger than what it is in the water science. Even though the people will argue that the amount of money spent on water projects is far greater. That may be true, but that is only for practical projects. That is not for doing research. Now, so coming back to really the...
Just ask a question for
Yes.
us to both of you.
Yeah.
What is the scale at which you would like soil moisture information to make good drought prediction? Is it 1 kilometer?
Well, no, I think it will have to be much smaller. The problem with soil moisture is that the soil texture and structure vary so dramatically at a very small spatial scale. Now, of course, at the moment we don't have soil moisture measurements even at larger scale. If you really look at the country as a whole. In the United States, we have soil moisture measurements, maybe in certain local areas and certain regions, but not like what we have in the case of rainfall or discharge. This applies to water quality as well. Partly because it's quite expensive. So water quality we don't have. The other area, in the case of drought, much of our emphasis has been on surface. On stream flows, on rainfall and soil moisture. But we have really not touched upon groundwater drought. This is also a very serious issue, and groundwater drought is triggered primarily by the withdrawal of water from the aquifer. So there also, there is a serious drought that is occurring, especially in Texas as well as in the neighboring states, and I'm sure it might be the case in other states as well. So the measurement is really a serious issue, and I could not agree more with Levent.
But Professor Kavas and also somebody from the applied end, Mark, what would be your thought?
Well, we're currently using a combination of obviously what's available, maybe not aware of some of these other models you were speaking to earlier, and including the VIC and the NOAA and Mosaic and Sacramento models that the Weather Service uses. The NLDAT stuff that does some of that runoff estimation as well as the soil moisture is what we currently use. I would say that to me the natural, when I say in situ, I am speaking the same as Vijay as far as observations of soil moisture. I think you said a good point was if you know what you're looking for. To us, the proxy is something like this veg dry that looks at, because vegetation is a natural indicator of evapotranspiration, soil moisture, things of that nature that give us an idea of stress on the natural vegetation or state. That's the one thing we look at. I'll talk about veg dry a little bit tomorrow and what's in that model. But the other last point I'll make, the other one we've been working with Goddard's Space Flight Center on is this GRACE satellite that's gravimetric that does go down. It takes the whole column, it's all the way down to groundwater, and it's very coarse and it's relative. But when we've worked with them to look at it compared to the drought monitor, the patterns are eerily similar, and we weren't using them as an input. So it's not like they used us to verify or we used them. It was done independently, and the patterns are spot on when you do animations with the drought monitor. So it's very, very interesting that works. Now it's very coarse. It's not temporally at where we need it to be, but it shows potential, and it's not just the top 5 centimeters. So.
Any thoughts? Mike,
Yeah, it's very comforting to know that, there are new remote sensing technologies coming in. But coming back, to your question about what scale, is appropriate. First of all, let me just mention, that neither the Sacramento, soil moisture accounting model nor, the NOAA land surface model, are really physically based models. To qualify to be, as a physically based model, all the parameters, of the model must be linked, to the physical land characteristics. In other words, they should not be basically calibrated or fitted in some way to fudge the model to the data in order to claim, that your model is working. That is the game, that's really played, as a standard practice in hydrology. The models such as, for instance, in NCAR's, land surface parameterizations, when they are considering, even 1 kilometer, grid resolution, and when they are looking at the soil, for instance, they will take, soil layers. They'll take 3 layers, 5 layers, things like that. But you know what? Who knows, where those layers are? In practice, if you go to soil surveys, within that 1 kilometer, by 1 kilometer grid, you are going to see, maybe 100, different soil, surveys, each, with different number of, soil layers. So fundamentally, everything is being fudged. That's basically what's happening. Okay?
So how do we get these other models exposed and out there? Are they operational? Is that something we?
Yeah. So some of these models are operational. In fact, they are being used all over the world. It's just that, they are not adopted, by NCAR or, by USGS or, by National Weather Service. I mean, those models are out there, And the point is, they are not, mainstream models, if you like, okay? The issue of, the soil layers, coming back, to your question, for those of you, who are soil scientists, actually know that even, over a 40 feet by 60 feet soil, you are going to see tremendous amount of variability. So the real question is, practically, how one can approach this problem. If you are going to be looking at it, as a watershed, looking at the water resources, as a watershed, then, one goes, to the hill slope scale. So at the scale of the hill slopes, then, one can try to basically average out, the variability. And the hill slope scale usually is about 100 meters, roughly speaking. So a representative, grid, would be, around 100 meters or so, would be more or less,
I suggest we try some of these questions, see how fast we get through them, and we'll come back to the audience. Is that okay? So I'm going to just pick them up at random, and I'll have, Jim, I'll have you get started with this one.
Oh,
Read it out aloud with the mic so that everybody can hear it, and then we will see.
For estimation of water footprints, when should ET be classified as recycled water? They say.
Jim, why don't you take that?
Yeah, that's right. Yeah. Answer is yes, we should. Yeah, that's it. And I can only speak in kind of the Midwestern point of view on this, but I know that with kind of the typical summer Midwest, it's hard to put an exact number on it, but I think it's something like 40 to 50, 60% of the water is recycled locally, and it's, it kind of depends because there's individual situations can make that vary quite a bit. So yeah, there is a fair amount of recycling, and of course, once you lose the ET, then that's another positive feedback into drought. So that's a good question.
In the case of non-irrigated crops, rainfall happens anyhow, and then that means used up by the plant.
Mm-hmm.
But in the case of irrigated agriculture, we need to be careful. We need to be accounting for the water. For instance, we had a project with Bureau of Reclamation to obtain ET through remote sensing in Palo Verde Irrigation District. Los Angeles is buying lands in Palo Verde Irrigation District so that they can follow it and take that water to Los Angeles. So that water is real, you know, it's the usage focus shifts and, but that needs to be accounted for.
Yeah.
Can I ask you a question about that? When you say, when you mention 40 to 50 to 60% of the water is recycled, are you talking about the state of Utah?
Well, it's purposely vague with the scale there. So kind of the Midwest.
So at the continental scale.
Well, actually, no, smaller scale. I would say,
Humid.
yeah, kind of a
summer.
Midwestern. So like for example, if we were talking about West Lafayette here, I mean, it's probably within 100 or 200 miles of where most of that would be coming from, maybe a little more than that. But, and I say 40 or 60% because it's, I've never seen an exact number, and it's very hard to there's been some modeling studies that kind of looked at that, but it's not exact.
I think that this,
I was just saying real quickly that the Pedicle-Padelfer boundary that we refer to as the 100th meridian, that PET equals precipitation is about in central Nebraska. From that point west, you're at a deficit. From that point east, you're at as a positive, and the ratios are going to change accordingly, shift. As in the Dust Bowl years, that moved from around Kearney, Nebraska and central, all the way to Des Moines, where the PET equaled P. So that was kind of a shift of hundreds of miles that you could see in extreme cases.
So how are warming temperatures going to impact that?
So that would be one thing to consider in a changing climate, and from south to north,
Yeah.
not just
So
east to west to east.
the data that all of you highlighted, what's the reason that you don't say ET monitoring is important? Or is it implicit that is always important? Because if you look at the data, number of ET stations, they're actually falling dramatically. I don't know how many ET stations are in Illinois now. Indiana, I think we have a couple of that.
I think I can count them on one hand, all the pan evaporation and.
Nebraska has none now. I mean, the network was disbanded.
Oh, okay.
Yeah.
And that's pan evaporation, which isn't really ET, that's just kind of the E part of the equation. I mean, really, to do ET, you'd have to have like equal covariance towers and stuff like that, so.
It is very important though. I mean, from
Yeah.
a climate change perspective, we talked the SPI, and the reason it's not effective is because it doesn't have temperature, is the use of the new index called the SPEI out of Spain. You know, we've worked with them. It's still a thorn thread, of course. It's still estimated, but that's still a very important issue. ET is still a big one.
at least from an agricultural viewpoint, that is really very fundamental. But I think coming back to, let me make a comment here, GS. You know, this whole concept of recycling is somewhat ambiguous, because the social connotation is that it is going to come back to this pretty much the same area, perhaps after a certain period of time, or perhaps instantaneously. But if you really look at the globe, say for example, in monsoonal climate zones, where for nearly 8 to 10 months of the year, it does not rain at all. And then during the monsoon season, perhaps for 2 to 3 months it rains. But it rains not because of the recycling of water through ET mechanism. It rains because of the monsoonal advance from, for example, in India, from the Sea of Arabia along the western Ghats, and of course from the Bay of Bengal along the eastern Ghats. And that is, you know, so really the monsoons, that is where they originate, and when they start traveling inward, that is when really we receive rainfall. So there, I don't think the concept of recycling of water through the ET mechanism will hold at all. So it all, you know.
So in those kind of regimes, if thinking about the total seasonal rainfall is almost an overestimate, because if that rain has fallen twice, say, or 1.5 times, you actually have, in a sense, less available water
We have less
than the
available
seasonal
water.
total rainfall would be.
Yeah, we have actually less.
Yeah, Steve Hilbert from the Midwestern Regional Climate Center, just to add to the happy thought list, I think that was Chris had up there earlier. The CocoRAS program is starting to experiment with ET measurements. And I think eventually the hope is that there's actually a network of ET measurements across the country, but it's very early stages, and using the same instrument I saw pictured in your photo there with the manual one. So that could be a possibility in another year or 2 or 3 that we have a lot more ET measurements around the country.
All right, we'll go with another question here at random. Let's see, this time we'll go with Chris to read out the questions.
Uh-oh. 2 questions. What is the physical meaning of the drought classes D0 to D4?
I think that should be
I think we have to give them more.
Answer that one first, or capitalize it the second.
Yeah, or why,
Yeah.
why do we have 5 drought classes, D0 to D4, and why aren't they called D1 to D5?
And actually in Texas, we'd be in D5, right, Brett? Bigger, everything's bigger in Texas, right? D5T. Actually, there was a reason we did that. And actually, D0 is not a drought class, so there really only are 4 drought classes, right? D1 through D4. D0 is abnormally dry, which is sort of a precursor. It's at the 30th percentile. Talk about this tomorrow a little bit more. When we developed that product, this goes back to what Vijay was talking about translation to the public. We chose something they were already familiar with. We looked at the Vegeta scale for tornadoes. We read the hazard literature and in the hurricane classification scheme. The public and decision makers want one map and one number. D1 through 4 is pretty simple. All right, you don't have to do. They could care less about all the models and everything. The trouble is they believe it, right? You know, so we get calls from senators and congressmen and governors all the time. Why is this D2? And we have a complex spreadsheet it doesn't even fit in Excel. It's custom made because of too many fields and too many records. But the bottom line is you have to explain to them that at the percentile thresholds that and I don't know who asked this question. I'll explain it a lot more tomorrow. If you're going to be here tomorrow, tell me now so I don't have to go into this right now. But will you be here tomorrow?
Yeah.
Okay, I'll explain it more tomorrow. But there is a triggering that we use based on percentile ranking approach. That way we can compare different parameters with different lengths of record. It takes out the unit issue because we have some parameters we don't have 50, 60 years of data. We have 20 or 30. So that's why we did what we did. And it does resonate, and I think you'll see it on the Weather Channel all the time. And that's why the decision makers like it, because it's simple to understand.
Thanks, Mark.
Yeah.
Dave picked the next question, so he'll give it to you.
Oh, yeah.
Whoever wants to take this one.
Just move down the table.
Yeah, that's right.
Is there a relation between oil resources and drought? Will it severe the drought? I don't know.
I'll make an answer. I'll make an answer up.
Is there a substance?
Yeah. Well, I mean, just some couple ways to answer this question. And of course, obviously, we've talked about many links between, greenhouse gas emissions and how that could be increasing the frequency of drought, certainly increasing temperatures. And that's a pretty obvious one. And then in the food security, results that I presented, there's a big increase, there's a big relationship between just the price of oil and the price of food and essentially drought in many forms around the world in the sense of lack of food or lack of access to water. Vijay, that was really interesting to see the links between energy consumption and water, both ways. So there's a lot of tie-in between those two things. And so I think that, as we run out of oil, that's going to make it harder to produce water and food. And as we burn more oil, that's also going to have negative impacts in the production.
Happy thoughts. Technology will save.
Happy thoughts.
Yeah, that's
Exactly.
right.
It's a fertilizer.
All right. Any burning questions from the audience? Yes. Okay.
Oh.
I mean, I think the question was like,
Yeah, sorry if I misunderstood it.
okay, the question is like, I mean, if you see the oil-rich countries, they are very dry,
And similarly, like if you take, I'm from Ethiopia, southern, the eastern, the Somali part, they said that, I mean, there is some kind of oil or something that they are exploring it. So is there any link with the presence of oil fields? Like if you take Texas, there is huge oil mining. And
Interesting.
I mean, is there any link with drought?
Yeah, it would be past by now.
Yeah, that's right.
I don't think I'm smart enough to answer that. I guess.
Is it generally true that all oil-rich areas are also dry? At least on land, let's say.
Well, you know, but
No.
oil essential Canada
Yeah,
in Alberta.
Democratic Republic of Congo,
So it's not
right?
really quite true.
I mean, there's
Venezuela.
yeah, Venezuela. Yeah.
And then, of course, we have a lot of oil in the ocean. But even in the land area, there are areas
Syria.
which are not really as
Yeah.
dry. For example, Alberta, in oil shales, and also in Midwestern U.S. So
Hands raised from the audience. Yeah, go ahead, please.
Hi. Okay, so I have a quick question. So I've seen some recent studies to use GRACE satellite data to monitor drought from a groundwater level perspective. So, and in their papers, they claim that the U.S. Drought Monitor should incorporate GRACE satellite data and develop an index based on GRACE. So how do you think that, if it's feasible and if it's necessary to do that?
Mark, it's all yours.
I work with Matt Rodell on that project, actually, and is it feasible? We're still looking at it. What they're trying to show is using that with GRACE and without, can we quantify how the drought monitor would be different? The problem with GRACE is the temporal signature, but for groundwater, that might be just fine. I mean, there's an inherent lag with drought before it impacts groundwater anyway. It doesn't happen first, it's agriculture first. And so I think there's some potential there, but it's also very coarse resolution. We're talking degrees, not meters or kilometers. We're talking degrees. But there's some new work that they're doing to try to get that down to, I thought I heard 40 or 50 kilometers. So there's some new stuff on future platforms, but who knows? With satellites, they're very expensive, and the new platforms they're developing. But GRACE has some potential. It's at a different time scale than the drought monitors weekly. In fact, the GRACE, if you read that paper, I believe if it's the one I think it is, we're actually using it for the North American drought monitor, which is a monthly product, and right there it fits very nicely.
Yes, right next to you, yeah.
Howard doesn't even get up.
Yeah, it's pretty interesting question about the oil and the drought. Because I'm thinking, because I do the relationship between the aerosol and drought. So it's like, do you think like in Texas, maybe it has a lot of oil refinery and like maybe Ethiopia that, I don't know, it's like, as you said, like omega block that cause the drought. Have you ever investigate like what else that cause drought, like more drought? Is that possible that more aerosol loading in the Texas area or the Ethiopia can cause more drought?
Yeah, I have not really looked at that. That looks like a very interesting topic to pursue. So I couldn't really respond if there is a relationship between aerosols and the drought occurrences. All that we know is that the droughts seem to be on the rise. Their frequency seems to be increasing. Now, on the other hand, if you go toward, for example, east of Texas in Louisiana, that is not the case. And Louisiana is the second largest oil producing state in the country and the first largest gas producing state in the country. And so that counteracts the point that you are trying to make, and Louisiana, especially along the Gulf Coast, has the second highest amount of rainfall in the country. So it's hard to say. Now, I think it may have something to do with with the history of climate and history of geology. I really do not know, but whether there is a relation. Now, through the GHGs, the greenhouse gas emissions, obviously one could
one could perhaps, make some comments, but whether there is a one-to-one relation, I don't know. Maybe Mark, you might.
Actually, I'll just say quickly,
Maybe Chris.
yeah, attribution is very difficult, short scale or long term. I would say with the warming climate and a warmer atmosphere should theoretically hold more water, right? We should have more rainfall, but the thing is the extreme events we see is the time in between events. And so we might have more water in the atmosphere and it might rain more, but it might rain more and run off because it's not as effective. And it might take more days in between events before we see rain. So, Chris?
Speaking to Kenya and Ethiopia during the spring, while this is contested, a lot of my research for the last really 6 or 7, 8 years suggests really strongly that for that season in that location, that the increasing drought frequency there is really tied to warming in the central Indian Ocean. And I think that we've shown that pretty convincingly. And then you come to the question of, is the warmth in the Indian Ocean tied to greenhouse gas emissions and aerosols? And all the coupled models suggest that probably about half of that warming it seems attributable to greenhouse gas emissions. So you can't. It's not a slam dunk, but there's a really strong chain of causality that would lead from greenhouse gas emissions to decreased rainfall.
And I'll just add to that, to the question, I think Matt has a point to add, that if you look at some of the work that Ramnathan and Rosenfeld and others are talking about, in fact, the droughts in China, they think is a black carbon affecting the cloud efficiency of rainfall. So certainly in some parts of the world, the soot particle, the black carbon, is highly attributable for some of the rainfall deficits. In fact, Brett might be able to attest, Nelson Gammon and some of the others work about the petrochemical pollutants going into the clouds and changing that from rainfall to lightning rather than rain has been some of the issues that we thought that
I think, can I add? I might add, Dave, few years ago I read an article published in Current Science, and that article dealt with the effect of dam construction activity inland, and as a result, a reduction in fresh water in Indian Ocean, both the Sea of Arabia as well as the Bay of Bengal. And the gist of the article was that as a result of reduced freshwater inflow into the sea, there is a direct impact on the monsoonal activity. Because they say the monsoons normally are generated within a narrow belt of no more than about 100 to 200 miles from the coastline. And because of the changes in the salinity patterns as a result of blocking freshwater supply to the ocean, apparently the monsoonal activity is undergoing a change, which in turn is resulting in the changing patterns of floods and droughts inland in the Indian plains. Now, whether there is any connection or not, but that is what actually the article, and this was written by a meteorologist and a coastal scientist and a hydrologist from the University of Colorado Boulder. So,
Two more questions. Oh, you have the mic. 1, 2, 3. Two more questions. First question about the dislocation. For example, in China or in Africa, they cut a lot of trees. So without the but right now, do we have any drawing that can see this kind of issue? Because we change the values, change the energy and water budget. So right now, current drawing that cannot reflect this kind of issue.
Well, I'm just going to give my personal opinion about. I mean, I think that those things can be really important, especially affecting the microclimate. But my personal approach to these problems is to follow the energy. And so, for many years in the Sahel, there was this big decline after the 1960s, and people considered a lot of different things and thought it might be desertification and deforestation, And really, I think it's pretty resoundingly concluded that it has a lot to do with this big change in the sea surface temperatures in the Atlantic. And so, at least for my little area of expertise, Eastern Africa and the Indian Ocean, if you look at the Indian Ocean, the thermal energy that has increased, over the last 50 years is just ginormous, And so, I've been looking over the last year at the increase in evaporation from the Indian Ocean. And over the last 30 years, it's gone up by something like 50 to 70 watts per meter squared. And so it's just this huge, I call them evaporative windows. It's just this huge flux of energy up into the atmosphere that's pretty likely to do something. And so, not that these other things can't have an impact, but if you just look at the energy and think about the thermodynamics of the atmosphere, at least for that system, it's pretty compelling.
Yeah, I have a simple question. Like, the question is, are we declaring drought effectively? Because we are using like SPI and PDSI to monitor drought, because SPI is simply based on the precipitation driven and PDSI is based on more like water balance models. So let us take an example. There are two regions, region A and region B, and they are having the same amount of precipitation. And region A having more water demand in terms of industry, agricultural, as well as domestic. So if they have the same precipitation, then we declare that both region is undergoing either severe drought or moderate drought. But if we see are the little deficiency in precipitation, that will impact more on the region A, because the water demand is very high and there are a lot of users. But when we declare the same type of severity in both. So is there any way to get to the address?
And then Jim, maybe you can chime in too. At least from our perspective, we built a database at the University of Nebraska, where I'm from, at the Drought Center, that looks at what states use which indicators as triggers. So we have that, if anyone's curious. That was part of a NIDIS activity we've done. Most states don't use just one indicator like the SPI or Palmer. They're going to look at anywhere from 3 to 5. Some of them now are starting to use the drought monitor as well, because they've had input into the drought monitor. So it depends on that factor, but as far as your question specifically for region A and B, that's where I'll talk about this tomorrow a little bit. What I think makes the drought monitor so unique is it's not just a quantitative number, but rather there's input from folks on the ground. We have a network of over 300 now experts representing almost every state. They give us an idea to the impacts that are occurring, because not all indices reflect reality. If my index says -3 and there's no impact, there's a famous person in our field called Kelly Redmond. Is there really a drought if there's no impact, right? Conversely, on the man-made issue, or the human-induced anthropogenic drought, where demand is the issue driving it, we will not depict that on the drought monitor. So we choose not to show that, because that's not a physical reason. It's just like if a tanker train was going by this huge reservoir in California and it derailed and dumped all the pollutants into the reservoir and they couldn't use it. Is that drought? Not physically, but it's a drought because they can't use the water from the reservoir. So that's some tricky semantics there. That's what I would say. And Jim, I don't know, from your experience with Illinois, trigger-wise, I mean, you don't use just one.
That's right. In Illinois, we don't, or in probably other states, we don't use one. It kind of the same reason that you're describing there. We use the drought monitor, and kind of sanity check, look at other impacts as well. And the thing is, a lot of the precip-driven indicators, sometimes the year can be very good, and other times of the year maybe not so relevant. Sometimes we get what I call paper droughts in Illinois, where if it's the late fall, winter time frame, it really doesn't impact anybody.
Right.
It doesn't even impact stream flow or anything like that. So it looks bad on paper. Some of the indices look bad, but it really doesn't have any impacts. On the other hand, you can have something in the midsummer where hot, dry weather combined could maybe have a major impact on crops or something that the drought indices are actually slow to respond to, and even state climatologists are slow to respond to, so.
It's our nature to think it's always going to rain.
Yeah, that's right, yeah, eternally optimistic. So
I would say one of my other drought spiels is always real estate's about location, location, location. Droughts are also about timing, timing, timing.
Yeah,
So,
exactly.
All right, one last comment or question, then I want us to adjourn.
Yeah, again, I'd like to address this issue, of where to take data, the in-situ data, and, the variability issue. I was just wondering whether DRENet is collecting and doing, any statistical analysis, on the soil survey data. Because the soil survey data that has been already collected by USDA is a tremendously valuable data set. I'm talking about, StatsCo and SURGO data sets. Utilizing such data sets, actually one can quantify the variability, and one can do an analysis of variance. And since, they specify, the texture classes, and since they have also related the texture classes, to the soil hydraulic properties, actually that data is, for modeling purposes, is an extremely valuable, useful data set. So I was wondering, are you people collecting such data, and are you doing, any analysis of that data?
Right now does not house the soils data because they're already available in other databases. And at least I'm not sure that any of us are using soils data right now.
For the LDAS run, we have to build it up for the StatsCo database. But taking your point beyond just the, one of the things we're trying to look into is taking that data, then some of the agricultural crop bulletin data, and then trying to correlate some of this information with yield data that is available in GIS mode. That's something we are planning, we haven't implemented yet.
Because it addresses the question that we asked earlier about, what scale should you be measuring is very much, involving the actual variability of those soil texture classes.
I'll make one comment to that. In VegDrive, Vegetation Drought Response Index, that I'll talk about tomorrow briefly, we use StatsCo currently in that model, but we want to use SURGO. When we first started that project 6 years ago, we didn't have, not all the country had all digitized SURGO. It was about 80% complete. Now it's almost all complete. We use it for the polygon that our in-situ observation sits on to determine the water holding capacity to drive it. So that's how we use it. We're not using all the polygons within, say, SURGO. In our new model, we actually use the station over SURGO polygon for a dominant map unit, not StatsCo. So we are trying to capture some of that water holding capacity variability using SURGO as best we can.
I think with that, we will sort of conclude this session right for now. I do want to point out that we did not go through all the questions. Talking to Carol, we will post these on DRYNET in some YT form so that the panelists and others at your leisure can go in and add your thoughts or answers to the question, and then all of us can look at that information.
Does DRYNET have a Facebook page?
Are you friends on it? DRYNET friends?
Well, I was thinking we have a question and answers that you can post a question and then people can freely, you don't need to sign up an account or anything, you can just go, I assume you can just go in, and I've never tried it, but I'm going to try it after this. So we'll do it that way as a test. And I'm sure people have a lot to say, especially tonight since you're away from home and don't have anything to do.
Any other questions, if you hand them to us, we'll post them. Right now, I really like for us to go and do the posters and talk about them, because many of you have spent a lot of effort preparing those posters. And we go for dinner at 6:30.
So 6:30 is the start of dinner, and same place as lunch, West Faculty Lounge. I don't know what the menu is. So,